Welcome to the Vector Academy. Let's look into monoids. The basic objects of algebra. Topics covered. Law of composition. What is a monoid? More general laws of composition. Commutative monoid. Some product rules for monoids. Subset of a monoid. Submonoid. Law of composition. Meaning of law of composition. Let S be a set. Let phi be a binary operation on S cross S. Here we will consider only two operations: addition and multiplication. If x, y are elements of S, the image of the pair x, y under this mapping can be a product of x and y denoted by x dot yn. A sum of x and y denoted by x plus y. A mapping phi from S cross S to S is called a law of composition. That is, when binary operation is applied on S cross S, we get a result which lies in set S itself. Example of law of composition. Let S equals -1, 0, 1. Then S cross S equals -1, -1, -1, 0, -1, 1, 0, -1, 0, 0, 0, 1, 1, -1, 1, 0, 1, 1. Let phi be a multiplication operation. Then mapping S cross S to S holds. That is, -1 cross -1 equals -1 which belongs to S. -1 cross 0 equals 0 which belongs to S. -1 cross 1 equals -1 which belongs to S. And so on. Associative rule. Let S be a set with a law of composition. That is, mapping S cross S to S holds. If x, y, z are elements of S, then we may form their product in two ways: xy inside brackets z and x, yz inside brackets. If xy inside brackets z equals x, yz inside brackets for all x, y, z in S, then we say that the law of composition is associative. Unit element. An element A of S such that Ax equals xa for all x in S is called a unit element. In most cases, the unit element is 1. When the law of composition is written additively, the unit element is denoted by 0, and is called a zero element. An unit element is unique. For if A' is another unit element, we have A equals A equals A'. By assumption. What is a monoid? A monoid is a set G, with a law of composition, that is a mapping phi from G cross G to G holds. Let n be the natural numbers. Then n is an additive monoid. A law of composition which is associative. If x, y, z are elements of G, then xy in brackets z equals x, yz in brackets for all x, y, z in G. Having a unit element, so that in particular, G is not empty. An element A of G such that Ax equals xa for all x in G. Order of product of elements of a monoid doesn't matter. Let G be a monoid, and x1, xn, elements of G, where n is an integer greater than 1. We define their product inductively. We then have the following rule. which essentially asserts that we can insert parentheses in any manner in our product without changing its value. The proof is easy by induction, and we shall leave it as an exercise. Empty product is equal to the unit element. As a matter of convention, we agree also that the empty product is equal to the unit element. More general laws of composition. It would be possible to define maps like this. Using arbitrary sets, one can then express associativity and commutativity in any setting for which they make sense. For instance, if below mapping holds for general law of composition, that is, all the images of fx, y belongs to T. Commutativity then means fx, y equals fy, x, or xy equals yx, if we omit the mapping f from the notation. For associativity, we leave it to the reader to formulate the most general combination of sets under which it will work. Commutative monoid. If the law of composition of G is commutative, we also say that G is commutative or abelian. Law of composition of G is commutative means, for the mapping f from G cross G to G, all images of fx, y belongs to G. fx, y equals fy, x. Some product rules for monoids. Let G be a commutative monoid, and x1, xn elements of G. Let theta be a bijection of the set of integers 1, n onto itself. Then, a bijective function from a set X to itself is also called a permutation of the set X, that is, for every X belongs to set X, theta X will be unique. For example, x equals 1, 2, 3, 4, 5. Let theta be a bijection of the set X to itself, such that theta 1 equals 5, theta 2 equals 4, theta 3 equals 3, theta 4 equals 2, theta 5 equals 1. Which clearly shows the relation. We proved this by induction, it being obvious for n equals 1. We assume it for n1. Let k be an integer such that theta k equals n. Then, which, by induction, is equal to x, as desired. Let G be a commutative monoid. Let I be a set, and let F be a mapping from I to G such that f of I equals A for almost all I belongs to set I. Almost all mean all but a finite number. Let I not be the subset of set I consisting of those I such that f of I not equals to A. By product rule, we shall mean the product taken in any order. The value does not depend on the order, according to the preceding remark. Because it is understood that the empty product is equal to A. Let I, J be two sets. Let F be mapping into a commutative monoid, which takes the value A for almost all pairs I, J. Then, we leave the proof as an exercise. Let X be an element of a monoid G for every integer n0 we define x power n to be. So that in particular we have x power 0 equals A, x power 1 equals x, x power 2 equals x square, and so on. We obviously have x power n plus m equals x power n cross x power m, and x power n power m equals x power n cross m. Furthermore, from our preceding rules of associativity and commutativity, if x, y are elements of G such that xy equals yx, then xy power n equals x power n cross y power n. We leave the formal proof as an exercise. Thanks for your time. Please like it and share it in your circle. Subscribe to our channel, The Vector Academy, for more videos, lectures and tutorials. For more information, do visit our website www.thevectoracademy.org.